First, it's my pleasure to give this presentation at the KLEE workshop. We have been using KLEE a lot over the years in several of our projects, both for concurrent software verification and also for SideChannel verification. Today's talk is going to be related to a little bit of both. First, I want to thank my collaborators. I've learned a lot by collaborating with people over the years, and especially the materials that I'll be talking about today, I learned from them. I want to specifically acknowledge Daniel Guo, who is a former student of mine and also the driving force behind this particular work. Today, I will first start by explaining what SideChannel is, and then I will talk about a particular type of SideChannel, the cache timing SideChannel. And then I will highlight our method, the main ideas behind our method, and finally I'll present the evaluation results. I think many people started noticing SideChannel in 2018 when Meltdown and Spectre were reported in the news. And as you know that these SideChannel attacks affected many x86 processors, and these processors are widely used both in personal computers and also data centers. The root cause for this kind of attack is called cache timing SideChannel, due to a specific hardware feature inside the CPU called the speculative execution. But this is only one type of SideChannel. And you can see here, there can be many other SideChannels. For example, in addition to timing, you could use sound, heat, EM emission, power consumption, and even injected faults. They all can be used to deduce some sensitive information about a software program. Here, when people are talking about SideChannel versus the main channel usually refers to the input and output of computing system, the normal control flow and data flow. Well, the SideChannel will refer to these non-functional properties. But in today's talk, we're going to be focusing on timing SideChannel, and specifically cache timing SideChannel. Before talking about our work, I want to briefly review the technical background to refresh your memory about cache. As you know, cache is a small storage area sitting between the usually fast CPU and the relatively slow main memory. Suppose, for example, you want to load the value of a program variable var into the physical register of the CPU. First, the CPU needs to query the cache. And if the data is already in the cache, this is going to be very fast. However, if it has to go through the memory system to fetch it from the main memory, this is very slow. And the difference between the execution time can be used to deduce some information about your program. Here is a more concrete example. We have a function leak, and it takes a sensitive parameter as input. Suppose somehow this sensitive input is used to access the array. It can be used directly or indirectly to calculate the array index. Let's also assume that the first 64 bytes of this array, SBox, is already loaded into the cache before we execute the load instruction. Then in that situation, by measuring the execution time of this load instruction or the overall program, it is possible to infer something about the secret input. For example, if it is observed that this program runs very fast, take 1 to 2 CPU cycles, that means there is a cache hit. And the only way to get a cache hit, remember the first 64 bytes are loaded in the cache, is for the secret value to be less than 64. On the other hand, if this runs much slower, then there must be a cache miss. And that means the value of the sensitive input is greater than or equal to 64. So some information can be deduced from the execution time of the program. So this is the classic situation for cache timing SideChannel leaks, and this has been well studied over the years. Here I'm just listing some of the related work. There are many more, but you can already see that people have been working on formally verifying SideChannel leak-free programs for using static and dynamic program analysis, for worst case execution time, and also for quantifying the amount of information leaked. However, in all these prior works, the focus has been on self-leaks in a sequential program when the program is running along. So that's really the starting point of our work. We're thinking about running a safety critical or security critical program concurrently with some other threads. In that situation, will there be new leaks? What we realize is that timing side channel leak freedom, so this is a security property, this property is not compositional. This is very similar to the situation in concurrent programming. People usually say that threads are not composable, means that even if a certain computation is functionally correct, when you run it in a multi-threaded environment, it can still have bugs. What we found is that a leakage-free program we're running along may leak some additional sensitive information if it's interleaved with some other concurrent threads. Because the threads are sharing the CPU and the memory subsystem, and in particular, the cache. Next, I'm going to use some more concrete examples to illustrate the difference between self-leaking and concurrency-related side-channel leaks. So I'm going to use this program, which came from a prior publication where the user carefully designed the program in order to illustrate the nature of this classic side-channel leak. Here, K is the input, is the sensitive input. There are two branches. So on the right-hand side, you can see the control flow graph. Suppose we run the right-hand side path. This would go through three memory accessing events: a load of PK, a load of element in Q, and then a load of PK again. If we execute the left-hand side path, again, there will be a load of PK, load of a different element of Q, and then load of PK again. So in some sense, no matter which path you're going through, you're going to be executing the same number of instructions. So it may appear that this is a constant time computation, but it's really not. If you're using cache, the cache may have different behaviors. So in order to study the cache behavior, we need to map the program variables to the different cache lines. Here, for ease of illustration, we're using direct map cache. But in our actual implementation, the tool can handle set associative cache, which is the realistic case. Here, we also assume that each cache line holds only one byte. So then there is an easy mapping from the program variables to the cache lines. We have 512 cache lines. We have 513 bytes in the program variables. So the first 256 bytes in the array P are mapped to the first 256 cache lines. Then the next variable is mapped to the next cache line, and the remaining ones will be filled with the element of Q. But because there is an additional byte, so two of the variables have to share the same cache line, P0 and Q255. So that's the root cause of all the trouble. Now let's look at the execution. If we symbolically execute the right-hand side path, we will have, these are the cache behavior, right? The first one is a code miss, the second one is a code miss, and then the third one is a hit because PK is already loaded in the cache at the moment. And this behavior remains the same for all possible values of the sensitive variable K. Now let's look at the left-hand side path. Here there are two situations. First, let's assume that the value of K is between 1 and 126. Under this assumption, then we can study the cache behavior. Again, it's going to be miss, another code miss, and then a hit. And the reason is because PK and Q, they're allocated to different cache lines. Now let's study the third case, where still we're going to go through the left path, but we assume that the value of k is 0. In this case, the situation is different because pk and the q now occupy the same cache line. So the first one is a code miss. The second one is going to be a conflict miss because we have to evict pk from the cache and put q in. That's why finally, when we access pk again, it's going to be a miss. Now, depending on the value of the sensitive input variable k, we observe different cache timing behavior. That's a leakage. So if somehow an adversary can monitor the execution of the program and notice that the program is running significantly slower, then it's possible to deduce that the value is going to be 0, right? So in this sense, some information about the sensitive computation is leaked. This is the classic case for cache timing SideChannel. This has been well studied, and people even studied the leakage mitigation approach. Right here, for example, you could use a semantic preserving program transformation to eliminate this cache timing leak. For example, you could move the load here from line 5 to line 10. You're not changing the program behavior, but you're changing the cache behavior, because at this moment, you can validate that no matter what the value of k is, the cache behavior is always going to be miss k. So in this sense, it's truly a constant time computation. But this is only the starting point of our work. What we are interested in studying is, what if you run this leakage-free computation concurrently with another thread? Is it possible to trigger some additional leak? Our answer to this question is yes. And here is a scenario. We're going to use the same motivating example, but we will run it in a multi-threaded environment. We have 2 threads. Thread 1 is going to run this program. Well, thread 2 is going to be doing something totally independent, functionally speaking. Right? So thread 2 would be loading a variable called a temp. And you notice that this temp has nothing to do with the program variables in thread 1. So in this sense, it's truly independent in the sense of both control flow and data flow. However, they're running on the same machine, so they're sharing the cache. So let's assume the same cache mapping, right? But because we have an additional variable temp, it has to share the same cache line with another program variable in P1. Let's assume it's P1. Then we need to answer this question again. Can we infer something about the value of k by measuring the cache time behavior? Well, in this situation, it's a little bit more complicated because previously we have to only look at 2 program paths and the 3 cases. But when you're running 2 threads concurrently, there are many possible interleavings, right? In this case, even for a tiny program, we have 8 different interleaved executions. For each one of them, we have to look for all the possible values of k and then study the different cases. So symbolic execution becomes a lot more complicated. But let's just focus on one simple scenario, this one particular interleaving, where we start with thread 1, we execute 2 load instructions, and we do a context switch. And then thread 2 would load the temp, and then we switch back. Under this situation, we want to study the cache timing behavior. Right? We will assume the same cache mapping. But there are 2 cases. The first case is when the value of k is not 1. And this is the case where the first memory access event is going to be a code miss because q is not yet in the cache, so we're going to load it into the cache. The second one is again a code miss. And the third one is yet another code miss because the 3 variables are mapped to the 3 different cache lines. However, the last one is going to be a hit because pk is already in the cache. Now let's look at a different scenario where the value of k is 1. In this case, the first 2 are going to be code miss, but then the third one is going to be a conflict miss because they occupy the same cache line, P1 and 10. So P1 is evicted from the cache. That's why when we access P1 again, it's going to be a miss. So again, we observe this divergent behavior in the cache, right, depending on the value of the secret K. Again, if somebody do this measurement, they would be able to infer something about our program, right? So this is a new leak that is triggered solely by concurrency, by multi-threading. So this is really our starting point. We're thinking, can we build a symbolic execution tool to automatically detect this kind of leak? And for that, there are three technical challenges. The first one is, how do we efficiently find the right thread interleaving under which this kind of a leak will be exposed? The second one is, how do we model for each interleaved execution the cache behavior, inside symbolic execution? And the third one is, how do we compute the right value of the sensitive input K? Because in this case, not only the interleaving, but also the value of the sensitive variable is going to be affecting whether there will be a leak or not. So that brings us to our method, which is called adversarial symbolic execution, to try to overcome the three technical challenges. At the high level, we have a symbolic execution tool that has three additional modules in comparison with the standard symbolic execution tool. For example, we're using KLEE here. And the first component is called adversarial scheduling to address the research question, how do we efficiently find the right thread interleaving? The second component is called adversarial cache modeling to try to model the cache behavior within each interleaving. And then we have the third component, which is an optimized way of solving the logical formula generated by the symbolic execution tool to come up with the right value for the sensitive variable K. So together we put the three submodules into KLEE, we would have a adversarial symbolic exclusion procedure. So next, I'm going to go into more details for each of these individual submodules. But overall, what our procedure is really doing is take a concurrent program. In this case, the concurrent program would have two threads. One thread will be running a security critical application, the victim program. It could be a cipher program. And there will be some other threads. Right? In a realistic setting, for example, you could have a web server that is using multi-threading to improve the performance. So one thread may be running authentication, and another thread may be running some kind of data manipulation. Now, our method would take this concurrent program and start doing symbolic execution. We use adversarial scheduling to try to systematically go through the different interleavings. For each interleaving, we will use adversarial cache modeling to analyze the behavior related to cache timing. And we will generate a logical formula that will be given to an SMT solver, and we want to solve this efficiently. And if the logical formula is satisfiable, it means there is a cache timing leak. So this is really the overall flow of our method. Next, I'm going to talk about individual submodules. So regarding the adversarial schedule, what I'm going to do is in the next three slides, I will walk you through the basic algorithm, starting with the sequential symbolic execution procedure as implemented in any of the symbolic execution tools, including KLEE, right? But this is my way of presenting it. But we need to carefully design this adversarial scheduling module because we need to address two technical challenges. The first one is that the search space is really going to be very large because we have to simultaneously explore both the sequential branching and the thread interleaving. So if we're not careful, there is going to be an interleaving explosion. However, we also have an advantage because in this case, we're only looking for cache timing leaks. We're not doing functional verification. So in some sense, we don't really care about what the program is computing. It's possible that two interleavings may be computing different things, but their cache timing behavior may be the same. In that case, we would say that the two interleavings are equivalent in this sense. And if we have already inspected one, we could safely skip another because there's nothing new that will be uncovered. So in that case, we can use some domain-specific grouping technique to make this very efficient. So for example, even for this tiny program, we would have 8 interleaving. But as you can see, only one of them could cause timing leaks. So if we can do this very aggressively, we can drastically cut down the number of interleavings. So here, I will start with the baseline symbolic execution procedure as implemented, for example, in KLEE. But this is my way of viewing the symbolic execution procedure. I like to use recursive functions to represent the procedure. So initially, I'll start with an empty state stack. And then I'll start with a symbolic initial state as a 0. And this recursive function, same as C, is going to be invoked on each program state to get the next program state. So in a sequential program, you would have a sequential computation, you would have branching. For sequential computation, it's very easy. You just compute the next program state. You take the current state S, you take the instruction, and you get the next symbolic state. But if you have a branching point, if-else condition, then the next states will be multiple, right? You simultaneously compute all the next states, and then you recursively invoke same as C again. You do symbolic execution. You could do this in a depth-first search fashion, or a breadth-first search fashion, or a combination of the two, right? But this is for sequential program. What do you have to do to handle multi-threading, right? The answer is not much. You just need to do something slightly different here. That is very similar to how you handle branching in a sequential setting. For if-else statements, there will be multiple next states. But in a multi-threaded program, at some point, you may be able to schedule either one thread or versus the other, right? You can execute A from thread 1 or B from thread 2, A before B or B before A. These are called the interleaving points. At these type of moments, you would have multiple successors, right, in the next states. So similar to how you handle branching, you just try to compute all the possible next states and then recursively invoke the symbolic execution procedure. So this way you can handle multi-threading. What do you have to do in order to conduct side-channel analysis? And the answer is just modify this few lines inside the red box a little bit. So before we go through the next states computation, we first check if they're divergent cache behavior. Because as this moment, you must be accessing some global variables, right? So this memory accessing event, can it trigger divergent cache behavior? Means that for some input values, this is going to be a hit. For other sensitive input values, this is going to be a miss. If that's the case, then you have a timing leak. So this is the overall approach that we are using for adversarial scheduling. Now let's talk about how to efficiently cut down the thread interleavings. We would only create new thread scheduling at this thread interleaving point for certain memory accesses. This is when we have a symbolic memory access where we have two accesses that may create a cache hit. And only under that condition, we would be looking for an adversarial thread interleaving that would make this hit become a miss. So here is a more concrete example, right? We have two threads. First, we need to make sure that A1 and A2 from thread 1 alone, without the interference from the other thread, if they can have a cache hit, only under that condition, we will be exploring the interleaving. And in this case, we also need to make sure that the three memory accesses are close enough in the main memory so that they are going to be mapped into the same cache line. So by doing that, we can drastically cut down the number of interleavings. But for each individual interleaving, we're going to use our adversarial cache modeling to try to look for leaks. Here, we view the sequence of memory accessing events as as a sequence, right? As a sequence where we have A0, A1, A2, A3. Each one of them is either a load or a store instruction. And there will be an address associated with each one of them. Right? From the address of each memory accessing event, we compute a tag. So this is a notion used in cache modeling. So two addresses will have the same tag if they're close enough, their addresses are close enough in the main memory that they're going to be mapped into the same memory block. They will be put into the same cache. We also need this line, right? Two addresses that are very far away can also be mapped into the same cache line. Remember, in our motivating example, we have P0, we have Q255, right? They are far away, but they can be mapped into the same cache. So with these terms defined, we can talk about this symbolic computation, right? The cache condition for each memory accessing event with respect to the sensitive variable k. So we define this tau ik as a logical constraint. So this may appear scary, but it's actually very simple. So in order for AI to be a cache hit, you have to have another event, AJ, that happened before AI, such that the two addresses will have the same tag. Means that they're close enough that they will be put into the same cache line. So if you've loaded one, and the other is already in the cache. Also, you have to have another condition, means that between the execution of AJ and the AI, you cannot execute any other event that would access the same cache line, right? If that's the case, then the cache line will be evicted. You won't have a cache hit. So having explained what this cache hit condition is, we can now talk about how do we use it to verify liquid freedom, right? For a program, we view it as a function, f, that maps some sensitive inputs and some insensitive inputs to the output. In a cryptographic program, for example, K could be the crypto key, X could be the plaintext, and C will be the ciphertext. In this case, what do we mean by liquid free? It's when for each memory accessing event, AI, the hit condition, tau I, is going to be the same for all possible sensitive values. So either they're always going to be missed or they're always going to be cache hit. Put it another way, if there's a leak, that means there must exist two different values of this sensitive input, K1 and K2, such that one of the key values would make this a hit, the other one would make it a miss. So we encoded this as a logical constraint during symbolic execution. So here is a more concrete example, right? For this interleaved execution, every time we encounter a memory accessing event, we will be generating a hit condition. And then we ask the solver, is it possible to have either a miss or a hit, depending on the value of k, right? In this particular case, the solver would tell us that for the first three, it's always going to be a miss, no matter what the value is. Right? But for the last one, it's possible to have either a hit or a miss, depending on the value of k. So that's a leakage. Now we're ready to talk about the optimized SMT solving. Right? In this situation, we're going to solve this logical constraint. Right? Does there exist two values, K1, K2, such that one of them is a cache hit, another is a cache miss? There are two ways of solving this. We call it the precise solution versus the two-step under approximation. In the precise solution, you take this logical formula, you generate the SMT constraints. You have to make two copies of the hit condition. You have two copies of the symbolic variable. One is K1, the other is K2. This is exclusive OR because the result of this is a Boolean value. So the XOR is going to be evaluated to 1 only when one of them is a hit, the other is a miss. So you can directly solve it. It's precise, but it could be computationally expensive. So our alternative is, try to make it faster. We solve it in two steps. So first we take The first hit condition, we try to look for a value of K1 such that it's going to be a cache hit. If we cannot even find such a key value, we don't even need to go to step 2 because it's impossible to have a leakage. Now, when we find a concrete value of K, we use that concrete value, here represented as K1 prime. We plug it in, then we check for the second hit condition. We try to make the second hit condition a cache miss. Right? If this also succeeds, then we would have a concrete value for K1 and for K2. One is a hit, the other is a miss. And this would always give us a valid solution for the whole formula. And the only drawback here is that it's an under-approximation. So it's possible that the two-step solution couldn't find any value. But that doesn't necessarily mean that the whole formula solved in precise manner will not have solution, because maybe in the first step, the solver picked the wrong value. But this is going to be much faster in practice. And what we've observed during our experimental evaluation is that usually if there's a leak, this two-step solution is going to find it. So I'll come to that in our experimental result presentation. So that concludes our the presentation of our method. Now we're ready to look at the evaluation results. So for evaluation, we've collected a set of real-world cipher programs from many different open source libraries. Many of them are for so-called lightweight crypto. So they're designed for resource-constrained computing devices like IoT devices. But some others are for general-purpose computing, like from Linux library. Some of these algorithms are implemented in different versions, right? For example, AES are implemented differently in different libraries, and CAS5 and DES. So in total, we have 20 programs from 6 open source libraries. The size of the programs are not large. Right? The number of lines of C code ranges from 194 to 1,429. So these are small programs, but because they are crypto, they're computationally intense. And the sensitive input are usually the crypto key here. They can be 8 bytes to all the way to 24 bytes. So these are the symbolic inputs for symbolic execution. The memory accessing events in each interleaved execution could be anywhere from 19 all the way to 1,680. So here are more statistics of the benchmark, but I will just move forward. In order to set up these experiments, we have a 2-threaded program. One thread, like I said earlier, is going to run this cipher program that I showed in the previous few slides. The symbolic input is going to be the key or some other sensitive input. And there will be another thread that is doing, functionally totally different things, but because they're sharing the same cache. Here, there are 2 options. Right? The first one is for the address of the program variables in thread 2, we can use the address, the physical address, allocated by the operating system and the compiler, right? The default one. And sometimes it will be allocated to the same cache line as a program variable, and whatever it is, we're going to use that as the scenario, right? And then we will run our adversarial symbolic execution to look for different interleavings and to say if there's a leak. So this is one option. This is really the optimistic scenario. The worst case scenario is when you assume that thread T2, the program variables here, may be mapped to any of the cache lines occupied by thread T1. So this is really a predictive analysis, right? Even though in the current machine, the current compiler allocated in this way, but what's going to happen if another compiler on another machine allocated in a different way, right? Do you want to know what's going to happen in that case? So this is option number 2. We keep the address symbolic in this case. Again, we're going to run this adversarial symbolic execution with both precise solution and 2-step approximation. So here are the results for the option number 1. the fixed address. Out of these 20 benchmark programs, we've found 4 of them that have concurrency-related leaks. And so this is one. Here, if it's non-zero, it means that we've detected some leakage points. Also, we realized that by comparing the precise solution and the two-step approximation, the two-step solution is almost as good as a precise one, in the sense that they found the same leaks, but they are much faster, right? So from the execution time standpoint. Here are the results for the symbolic addresses, right? So this is really the worst case what-if analysis, right? What if the cache line mapping can be arbitrary, right? In that case, is the so-called leakage-free program still leakage-free? We found that in this case, it's much easier to create leaks in certain scenarios, right? 14 out of the 20 programs would have leaks. Also, by comparing the two-step solution with the precise solution, we found that the two-step solution works as good as the precise one. Sometimes you can even find more leaks because sometimes a precise solution would run out of time, right? There is a time limit set. So in that case, the two-step solution is going to be able to go through more interleavings and find more leakage points. So overall, the precise solution would actually time out in 9 of the 20 programs, but the two-step solution only timed out in 1 of the programs. So here is another way of showing the results for the option number 2. It's comparison of the detected leakage points. For blue bars are the precise one, and the orange ones are the two-step solution. And this is the computational overhead. And you can see that the two-step solution runs much faster. The only case where both methods timed out is a cipher called two fish. We looked at this one and we realized this is really a challenging case. This indicates that there is still room for improvement inside the symbolic execution tool. In this case, there are a lot of memory accessing events. And not only that, for the two-step solution, and you can see that in the first step, we can always find a cache hit case, right? Without the interleaving of the other thread is always a cache hit. So our two-step solution is always going to be looking for adversarial interleaving, but most of them are actually not possible to generate a leak, but that took a lot of time. So we feel that this is a point where things can be improved. To conclude, this is a new method for detecting cache timing leaks, specifically related to concurrency and multi-threading. Our experiments show that real-world ciphers, if you put it in a certain scenario that is running with some other concurrent threads, it's possible for it to leak some additional information. Well, we showed that these leaks are possible. These leaks are real under certain conditions. More efforts are needed to show that, okay, these leaks can be leveraged to really attack some real software system. But in any case, we're tool builders, so we build a tool that can be used for that. Every time we report a leak, we report the precise interleaving and also the value of the sensitive variable to let people double check that this is really a leak. That's really what I want to talk about related to cache timing leakage. But as I mentioned earlier, this is only one of the many possible type of side channels. For any of these other type of side channels, there is this question of how do you detect these leaks? Beyond the leakage detection, you can also have other interesting problems. For example, how is it possible to automatically synthesize the countermeasure, transforming a leaking program into a leakage-free program, and can you formally verify it? And if there's still leakage, can you quantify the amount of leakage and show that it's small enough in practice? So these are all very interesting problems. And the thing is, you can do this kind of research for each different type of side channel. So it's a really interesting field. So over the years, we have been working on some of these different side channels, and for some of these research uh, problems, we've published something, but we feel that we are barely scratching the surface. But if you're interested, here is a list of our related papers. And the three highlighted ones are related to cache timing. Others are related to other side channels. So that's all what I want to talk about today. I wonder if there are questions.